Welcome to MEI Numerical Methods Approximating Functions. In this video we'll be looking further at Newton's forward difference interpolation method. So this is what we were looking at last time, and we came up with a linear version of Newton's interpolating polynomial. Now here we see how the interpolating polynomial can be generalized to higher orders, and so the third term that we're adding on, instead of having that difference term there, we've now got the second difference term, which we'll be seeing an example of that in a moment. And then instead of the h on the bottom, we've got h squared, and in fact we could have written that as 1 factorial, and we've got 2 factorial there, and then 3 factorial there, and so on. And we're also going to use more points than we did previously, so instead of just having the x minus x naught bit, we've got, in addition to that, for the next term we've got x minus x1, and then for the third term we're bringing in x minus x2. And as already mentioned, this only works if we've got a constant h. So we're going to see how this works for these three given points, and so we want to find a quadratic to go through those points, and we also want to do some interpolation to see what the value of the function would be expected to be for x equals 2.5. So here we have the finite difference table, and we've got the second difference of 2 there, which goes into our formula, and we're using the first two x values, 2 and 3, are both needed in the third term. So then that can be simplified to x squared minus 2x plus 5. And because we've only got 3 points, we can guarantee that a quadratic will go through them, assuming the 3 points aren't on a straight line, which they aren't. Now, to find the value of the function at 2.5, it can be easier just to plug it into the original unsimplified version rather than having to do the simplification. So if we do that, we come up with a value of 6.25. Now here we have a more complicated case with many more points, and notice that as always, the x values are going up by a constant amount, which is 2 in this case. So this would be indicated by this notation here. So we're starting at 3, going up by 2, and then the last x value is 15. And so you might like to pause the video and have a go at creating the finite difference table in this case. So hopefully you've got these values here, and notice that in none of the difference columns do we get any constant or approximately constant values. So had we had roughly constant values as the first difference values, then we could have said that a straight line was an approximate fit to the data. Similarly, if the second differences had been roughly constant, we could have fitted a quadratic approximately, but as that's not the case for any of the columns, then because we've got 7 points, we can guarantee to fit a polynomial of order 6 through the points. So that's the best we can do, really. So in general, these are the situations that could arise if you've got 7 points. It could be that they all lie on a 6th-degree polynomial curve, and but it could also be the case that they happen to lie on a lower degree polynomial curve, and we could establish that by noticing exactly constant differences. And as an example, if you had constant second differences, then that would mean that you could fit a quadratic exactly through the points. But we might be satisfied with a good approximation, in which case we just want the differences to be approximately constant. So that completes this video, and we'll be looking at Newton's method further in the next video.